Coba biar nunggu IP ditanya aja dulu. Kayaknya udah dibuka. Oke. Iya kan ada. Oh iya.
Ada database-nya lagi.
Nge-vlog YouTube.
Gak pakai berapa student gitu?
Kamu?
Berapa student?
2 orang. Harusnya IP pegawai.
Oh iya, gimana nih udah?
Kalau disconnect kan cuma ini kan nggak apa-apa.
Ini aja ya.
Statistics or informatics, and then also we have background from social, demography, social, and then health, bioinformatics, economics, yeah, management, yes, of course, management, yeah. So in this maybe university or institution, yeah, maybe in this polytechnic, we teach for our students to be maybe in this polytechnic, we teach for our students.
Good morning, ladies and gentlemen. Thank you very much, Thomas, for coming and sharing knowledge in this special occasion, monthly discussion. And we will discuss about spatial data. I will serve as moderator this morning. So maybe we will start with your presentation first, and then we continue into the discussion session with the participants. And then we continue into the discussion session with the participants. And then we continue into the discussion session with the participants. And then we continue into the.
Be here. I've been in Bandung. Well, several people know that last week. I'm also very happy to be in Jakarta today. I'll fly back to Belgium tomorrow, so I'm going to enjoy my last day. I will start with some spatial statistics. So today I'll talk about spatial different analyses that I've done on spatial data, and I'll start with an introduction of the 3 basic types of spatial data. And then I'll show you studies in which I have worked with all 3 of them. Okay, let's start with that brief introduction. The first type of spatial data is what we call point pattern data. So spatial data, you can think of that as all types of data that have a geographical dimension and interpretation in space. At this moment, I'm only looking at 2-dimensional space, but you can go, of course, further in that. But these are all data points that you can locate on a map. That's the idea. And the first type is what we call point pattern data. And in point pattern data, you are interested in where events occur. So the example here is from a biological survey, but you can think of everything that fits within this context. It can be econometric surveys, health surveys, etc. So where do events occur? Suppose that you have a map here, and this is a map of a national park in Africa, and all the points that you see are locations of nests of gorillas, mountain gorillas. Those are big apes. They're very rare, and so researchers want to know where they are located, and is their location related to specific explanatory variables such as habitat type, the occurrence of specific trees, etc. What you assume here is that you know that you can have that you can see observations, that you observe all events that happen throughout the map. Other types of maps that this is typically used for are, for example, earthquake maps or lightning maps. All the locations where there were lightning. There's a very famous example where you have in China all the different places where there were lightning strikes, and through the observation of those points, you can investigate where the intensity of those points is highest, and you try to relate that with specific explanatory variables. So the important thing here with point pattern data is you observe everything that happens, and the thing that you are interested in, the event that you're interested in, is a location where the event occurs. That's the most important thing, location. So this is what we call point pattern data. Second type of data is what we call geostatistical data or spatially continuous data. So the difference with point pattern data is that in point pattern data you're interested in where do events occur. For geostatistical data, you go to a location that you choose beforehand and you are going to measure something there. Suppose that I'm going to evaluate biodiversity at specific locations in Limburg. Limburg is the province where I'm living in, so Setia has worked around here for 4 years. Because this is where the campus of Diepenbeek is located. 6 years. Oh, okay. So this is a province. It's not big, but suppose that you would go to, let's say, 100 locations within that province, and you would measure something there. Again, it is a biological example here, but you can think of all that you can use this in all different contexts. Again, economy, health, etc. The difference with point pattern data is that here you choose locations where you go to. At those locations you measure something, and while you are analyzing it, you're actually interested in what you are measuring at those locations, but you keep into account, or you take into account, that these measurements were done at specific locations, and these locations might be correlated. I mean, there might be a spatial correlation going on, because locations that are close to each other might not be independent. You all remember that for a simple regression model, you assume independence. Well, if you are looking in a spatial context, this would be a regression or a regression type of analysis, where your error term is not independent because you have a spatial dimension and you want to take that into account. So you're here interested in the thing that you measure at those locations, but you take into account that spatial correlation. While in point pattern data, you're interested in locations themselves. That's the difference between both. Now, in geostatistical data, or again, what I also told you already, spatially continuous data, you assume that you can go to an infinite number of locations. So in practice, these data are data where you have a GPS location, a specific coordinate of the location where you observe or where you do a measurement. There is a different kind of or a special case of these data, and it's what we call spatially discrete data or lattice data. So suppose that instead of going to a location, you have for each location a specific coordinate. You can also have data that are aggregated in, for example, a municipality, or like in a study that I saw in Bandung, where they have all sub-districts, and for each sub-district they have the number of dengue cases, because each dengue case is not related to a specific location. Those numbers of dengue, and this is not this example, but it's another example, so all the cases of dengue in that other example would be aggregated within a sub-district. So you have a special case here of the spatially continuous data. You have spatially discrete data because you have these lattices, all these different municipalities, and you mostly analyze this by assuming that there is some kind of correlation or dependence based on distance between the municipalities. And what we mostly do in these kinds of analysis is construct a neighborhood matrix. So who's a neighbor of who, and by using that neighborhood matrix, you can then take into account dependence. So there are three types of data: spatial data, point pattern data, spatially continuous, and spatially discrete data. So again, because this is very important for the spatially continuous and spatially discrete data, the spatial aspect of the data is not your major concern. It's actually a nuisance that you want to take into account in your analysis. You're interested in something else, but you have to take into account that there is spatial correlation. While in point pattern data, you are really interested in the intensity in a spatial dimension. Where are my happening? So that's a bit the difference between those models, or between those data types. Now, what I'll show you in the next where I go a bit deeper in these three types of data is first a study, and it's also, this map is coming from that same study. I'll discuss it a bit deeper in the coming few slides. So I'll first do a study about a disease in Flanders. So this is Flanders, the northern part of Belgium, and this is these are spatially discrete data. And in the second part, I will talk about geostatistical data, so spatially continuous data. And in that second study, I also analyze the data with a point process analysis. So I'll tackle all three different types, just to give you a taste of what you can do with these data. Okay, so I'm going now to my second slides, my second PDF, which is this one. So the title is The Spatial Combined Model for Over-Dispersed Zero-Inflated Count Data. It is as follows. I got the question from researchers in Belgium to investigate mesothelioma. I'm not sure if everyone here is familiar with mesothelioma, but it's a cancer type that is, let's say, like slowly. And suppose that you get exposure to asbestos, then it can take 30 years before you get the disease. And the thing is, in Belgium and also in other European countries, asbestos use is not allowed anymore, already in Belgium since 1991, I believe. But we still see a lot of cases still occurring now, so people who are diagnosed with the disease now, because the disease has a very long incubation time. And there are some insurance problems about that, because people who get the disease, they want to get some insurance from, for example, companies that used asbestos and then through the use of that asbestos exposed their workers to it 30 years ago. And so in Belgium it's a very hot topic. So the objective was, we would like to model the distribution of mesothelioma here, and we wanted to see if there was a link with historical asbestos use in Flanders. So mainly in the industry that used that asbestos. That was our goal, to see if there was a spatial correlation of the occurrence of that disease now and the locations of those companies that used it. Now, because the disease is very rare, because it is a very rare disease, but it's very deadly. We have lots of zeros in our data. If we look at data per year, or even over a few years, sometimes or often you have zero counts. So we needed something to take that into account. So we are going to look at an analysis where we take into account zero inflation, and then also spatially structured and unstructured heterogeneity. I'll talk about that in a moment. So that is the goal. The data that we have were yearly incidence counts of mesothelioma between 1999 and 2008. There are 308 municipalities in Flanders. By the way, I don't know, oh no, I did not show a map here yet. I have data for males and females separately, and like I told you, there are many zero counts. If you look at throughout all these years, so here you see the number of diagnosed cases per municipality per year, and you see that more than 5,000, around 5,200 so this is males and females separately, so around 5,200 of the 6,000 approximately, a bit more, are zeros. So we have huge zero inflation problem. Now if we look at some maps, then this is the map of Flanders. So you see here the males in 1999, here males in 2008. These are these are standardized incidence rates. These are the same years for females, so 1999 and 2008. And so what we show here are standardized incidence rates, which is the ratio between your observed counts and the expected counts, which are standardized for age distribution and age. It's here. So these are the expected counts are standardized counts. So you have to think of the standardized counts as being what would you expect if you take the information of all your municipalities, and you have your age distribution and the number of the population within each municipality. If you have that information, how many cases would you expect within this year? And you can easily calculate that number, but if you then take the ratio of the observed counts and the expected counts, and you have a high, that ratio is larger than 1, that means that there are more observed cases than what you would expect for that municipality. Now we have not modeled it then yet, because modeling will give us a better understanding of these data, but this is a very general way of looking at how incidents might be higher or increased in specific locations. Now, for example, Brussels, by the way, I have to talk about that as well. Brussels is here as a white spot, and we don't have information about Brussels because in Belgium there's a whole political system that makes that if you are analyzing data from Flanders, Brussels is not included. It's very strange. Another big city is Antwerp, which is located here. You see it here, Antwerp. And then, just for your information, this here is Diepenbeek, where Setia has been for 6 years. Now, there is one specific municipality that had a big industrial site that used a lot of asbestos, and we know this, and this is always in the news, and they had to stop their business in the early 1990s. But there is, or this is what everybody says, it has not been analyzed before, there is a high increased number of cases, it seems, around that area. And it was mainly of interest to see if we suppose that we would analyze this with a spatial analysis, we would predict our risk of getting the disease, then we would like to see if this comes out of it, that indeed the risk to get the disease is higher over here. So that's actually what we hope to see in the prediction maps afterwards. Okay, so suppose that your y are the observed counts and the e's are your expected counts. Those expected counts are the standardized counts. You have 308 municipalities, you have 10 years, and you have 2 genders. We assume the relative risks to be constant over time and gender for the purpose of this analysis. The reason being that when we did not assume this, we had some convergence problems. So we're using Bayesian statistics for this, based on MTC, and we had some convergence problems, probably because of the high number of zeros, and that's why we had to make some assumptions, and we assumed the relative risk to be constant over time and gender, such that we could actually use all data from each gender and each time point as some kind of a repetition of each other, which is in reality probably not correct. There will be some, well, this should be a bit more elaborate, but well, there was just no other way of going forward, so we had to take that assumption. And then we fitted what we call the combined model. And the combined model combines a conditional autoregressive, that's a CAR model, with a Poisson gamma model to correct for spatially correlated and unstructured heterogeneity. So that's a mouthful. It means that suppose that you have Poisson, so data that are Poisson distributed. Normally, you assume that the mean and the variance in the Poisson distribution is the same. Now, what we often see in real life is that they're not the same. And what is typically used to accommodate that is a negative binomial model. The negative binomial allows that mean and variance to vary. Now, a negative binomial is the same as a Poisson gamma model. So if you fit a Poisson model with a gamma distributed random effect, then the gamma random effect will take into account the extra variability, because mostly what we see is that we have over dispersion, which means that the variance is larger than the mean. You can also have under dispersion through zero inflation, but we are now looking at over dispersion. So over dispersion means variance is larger than mean. How can you accommodate that? Well, through a gamma random effect. Now, a gamma random effect does not take into account or does not assume that your extra variability is coming from the fact that you have spatial correlation, because spatial correlation can induce over dispersion. But it is better if you know that there is spatial correlation, that you fit a model that has a parameter that takes into account over dispersion, but on top of that assumes that it's spatially structured. So if you would like to do that, you can fit what we call a conditional autoregressive model. And a conditional autoregressive model, I'm not going into the details here, but it is an autoregressive model for space. You have to think about it like that. It's just you have a neighborhood matrix of all your locations, and you just indicate that the mean of a specific location also depends on the means of your neighbors. So you can introduce a conditional autoregressive random effect in the model. Now, you can either do the Poisson gamma, so with an unstructured heterogeneity term, that's the gamma part, or you can use a correlated, spatially correlated term, so for correlated heterogeneity, that would be the conditional autoregressive model. But you can also combine both of them, because you might think that a part of the over dispersion might come from the spatial process, but a part of it can also come from anything else, like which is not spatially it's not spatially correlated. And there is some debate about which model is best, because if you fit a model which has both the conditional autoregressive part and the gamma part, then you actually have some identifiability problems. And this is one of the criticisms that many people give to the method that I'm applying, actually, that there are identifiability problems. On the other hand, using this, where you allow for spatially correlated and unstructured heterogeneity, is probably in real life most realistic. And because we're interested in not in those random effects separately, but actually in our relative risks, which the relative risk here is theta times kappa. Because we're interested in that, most people do not really think or find the identifiability problem a huge problem, because we are looking at the scale of this theta times kappa. Now, in this model, so you have your y is Poisson distributed, is your expected count times your gamma parameter times kappa, and kappa is equal to e to the power, an intercept, no covariates in this analysis, and then your u, which is your conditional autoregressive random effect. You can introduce covariates, and actually it would be very worthwhile to do that. And I would definitely think of a covariate that gives us information about the exposure points of asbestos. That would be very helpful. The problem is that we did not have the information. We have information about Capelle op den Bosch. We knew that that city has factories that used asbestos, but we don't have a full idea about everywhere in Flanders. So we did not have a covariate to introduce into the linear predictor over there. So the relative risk, RR, is theta times kappa, and the rest is, I explained that, so you had your gamma parameter for uncorrelated heterogeneity, an intercept, and a spatial random effect for correlated heterogeneity. Now, this is a basic combined model, and I did my PhD, in my PhD I developed some spatial extensions of this. Now, you can also you can think of this model as taking into account these types of overdispersion, but on top of that, we here have a lot of zeros. So what people often use in a zero inflated case is what we call a zero inflation model. And there are mostly two types of models. The one that I'm interested in is the hurdle model. And actually what it says is that there are two processes in this model. So first of all, there's a Bernoulli process, which allows you to model the zeros versus non-zeros. If it's a non-zero, the previous model comes into play. So if it's a non-zero, it's modeled like this, right? So so this is a rather complex mixture, and it has, well, in theory, it has some very interesting ideas or concepts, because overdispersion can come from three sources: zero inflation, spatial correlation, and spatially uncorrelated heterogeneity. So three sources. And when I started fitting these models, I thought, well, we have so many zeros, this model will definitely do best, because this is designed to take into account zeros. And if I then have a spatial correlation term, a spatially uncorrelated term, etc., I will be able to disentangle all these different sources of variability and model the data best. So that is what I thought, but I'll show you what comes out of it. Now, you can again model this pi with spatial random effects. So you can think of that, suppose that we have a non-zero, so suppose that we're looking here and we go back here, suppose that we have a non-zero, there might be, for the non-zeros, there might be spatial correlation, right? But you can also think of the fact that the non-zeros versus the zeros, that might be spatially correlated. And that's realistic because the non-zeros might occur in regions, in specific regions that have the factories. Because I told you that the only risk factor of mesothelioma is asbestos. So you would think if there is no factory around, then the disease will not occur. But that's not completely true what we saw in the end, because some people, they do not live in the locations where they got the disease, so they have to drive home to another municipality. They get ill in that municipality, or they move throughout their life, and all of a sudden you see people or municipalities that do not have an asbestos history, they have disease cases, but those cases probably got it in a factory in another municipality. And my PhD student is by the way, analyzing or looking at methods to deal with that. So we can extend this this hurdle model to the combined framework, where we can, you can go in many directions with that. I, for example, did a analysis where the linear predictor of the non-zero cases had a spatial correlation term, and the pi here had a spatially uncorrelated heterogeneity term. And then on top of that, you're taking into account zero inflation, etc. So it was a complex model. And yeah, I thought that when I would fit this model, this would be great. But now this is the result, and there's a lot to see on this slide, and I'll briefly explain to you because I'll not go over all the details. In this model, so in the panel here, we fitted the model. These have a zero inflation part. These also have zero inflation parts, and these are the models without zero inflation. So these are models that are based. The lower panel is a model that is based on only this. The upper and the middle panel is a model that's based on this, and based on this means that it is a zero inflation model, but for the non-zeros it has this part. So you actually, if you're looking here, the upper two panels, they are the most complex models. These are what we call simple spatial, the typical traditional spatial models. These are the extensions that we proposed. Now, the difference between the upper and the middle panel is that in the upper panel we add here in the hurdle part, so the Bernoulli part, a random effect. While in the middle panel we don't do that. In the middle we only have like our pi is we keep it simple. We only have an intercept. Okay. And then if you look at the different columns, there are many things going on. This is a hurdle car gamma normal model. These are like, I do not I do not have time to explain everything here, but what I want to show you is that when we look at marginal predictive likelihood values, which is a method to look at fits of data or of models, we see that this model here, which is a conditional autoregressive model, a simple model, does much better than the very complex models that take into account different sources of variability. And the reason being probably that this model can take into account, through its one random effect, all the other sources of variability. So the model that I'm having here, wait, let me go back. This is the car gamma, this is the car gamma. So this model here is this one, is this one. This model here, the gamma random effect here, theta, It does not have this, but it has a normal random effect here. Another normal which is spatially uncorrelated. This one only has the conditional autoregressive part, so it does not have the theta, but it does not have anything else except it has the U, this is the car random effect, but not anything else. So what I've just shown here is that a simple model, even if you have spatially correlated heterogeneity, spatially uncorrelated heterogeneity, and zero inflation, a very simple spatial model can accommodate it, because it does not distinguish between the sources of variability. It will just look at like it will try to model over dispersion in the best possible way. And these values here, the lower values, those are the fit values, they should be as large as possible, and it's largest for this one. So it's interesting to see that while we would expect that these models do better, in fact the traditional ones do much better, and within the traditional ones, even a simple traditional one is doing better than the complex ones. Now, suppose that we would use this model now to predict, this is actually what I said before, so these were the best models. So this is the same model as before, so this is what I talked about here. So everything that is in here, is in here, I already told you. So, but suppose that we would now use that model to predict relative risk estimates, then we would obtain the following map. And we see here very clearly that the area around Capelle of den Bosch is very elevated in terms of risk of getting the disease, while there is like a cluster, there appears to be a cluster around it, and that's probably because the people who worked in that location, they also lived around that area, but not always in Capelle of den Bosch. So you often get people who develop the disease in another location which is close to that one. So if we then would look at which risk estimates are significantly different from one, then we see that there's a significant increase in cases here. So you clearly see that the relative risk around this area, around Capelle of den Bosch, is highly elevated. So this is what we got out of the study, and it was actually very interesting because I published it just at the moment that it became a hot topic in Belgium. So also this map has appeared in the press a couple of times, because people who were like living there, they were actually seeing, okay, we have an elevated risk based on a statistical model which tries to take into account these forms of variability in the best possible way. So this is yes.
What is that? You know that in the red one you have one white spot. See that?
That one?
Up.
Oh, this one.
Yes.
It's just
right?
yeah. It's one municipality where we could not show the. No, that was data, but so these are predictions from the model, and based on those predictions, we can obtain confidence intervals. And if the confidence interval does not or is larger than 0 everywhere, it's a 95% well, actually credible interval. And for this location, it included 0 still. So we could not show that there was a significant increase here. But it is interesting because everything around it has it, and this one does not have it. But I think it's a coincidence. I think that that there's no real thing behind it. And also this one here is one, I believe, this is Antwerp. It's one big city. So suppose that all the cases would appear here, then it would be like, it would be read throughout the whole municipality. This is a bit the downside of especially discrete data. You don't have a very high resolution, so you don't know where the cases are really appearing, so you average them over the whole municipality. And also there is an effect. This is something that researchers told us, that we had here the factory, but here is also the port. So all the material came in through here, and the people who were working at the port, they probably had to work with asbestos also a lot. So you probably have also some exposure over here, and that is probably the reason why you have this band of cases or prediction, like increased risk between this and this, because this was where the port was exposure, and this was where it was, well, the manufacturing happened. So yeah. So this was an example of an analysis, and it was a bit technical with all the different models, but this is an example of what you can do with spatially discrete data. And what I'll be showing you next is an example of spatial continuous data. So, and by the way, the conclusions are zero access models are not always preferred in zero access situations. So in many cases you can use a pretty simple model with not too many parameters to do a good job. Then one or multiple random effects can capture a lot of extra variability, often regardless of the underlying source of variability. And there was an elevated risk in the central north of Flanders around the Capella of the Bos. So those were the conclusions there. Now, I have another example. So this is the spatially continuous. This is another type of presentation, because in my spare time I like to draw, and so this is also a presentation that I often do for non-statisticians. It is a bit more technical here, but sometimes I leave out some of the technical parts, and then it is also useful for non-statisticians. So the idea here is mapping biodiversity using opportunistic samples. Should we trust our inferences? Again, it's a bit of a biological example. I'm always working in that. So for the people who are not really doing this, but my apologies, but it is still very useful. It's just another example, but it can be the same type of data in other cases. So the idea here is, suppose that we have opportunistic samples. I'll talk about that in a moment. Should we trust our inferences? Okay, what is happening? Is it loading? Was okay yesterday. Okay. I'm not sure if the version that is streamed has the PDF that is streamed. Does it have an image on the pages, page 2 and 3, etc.?
Yeah, they have the image shown.
Oh, okay, all right.
So it's not the PDF problem.
Okay. So so I talked to you about geostatistical data. So the difference between geostatistical data and point process data again was that in geostatistical data you visit locations and you measure something. So suppose that you would visit these locations. This is a map. You have these locations and you're going to measure something of interest. In a point process you would not know beforehand which locations to visit, because you're not going to visit anything. You're just going to see which locations have events. So in a point pattern analysis or point pattern process, you would have a blank map and then things occur on that map, and where it occurs, that's what is of interest. So, but here you visit locations and you are going to measure something. And suppose that you would measure something which can be anything, for example, the income of people throughout the country. And you have high values here. If it's darker red, it's high. If it's less dark, it's low. So suppose that if you would look at this, it seems a bit that in the northern left corner it is a bit higher than down here. Anything that you are looking at as an example. Now, in a geostatistical model,